actually. Yeah.
Yeah, I
So
wasn't okay. Then
yeah,
just
I think we are all set. Professor Suvrat, you're ready with the talk. We have tested it, and Professor Gopakumar, are you ready? Then we will start the streaming
sure.
on YouTube.
Yeah.
Okay, Gopi, you can start the streaming over there and let us know once the stream is up.
Yeah,
Then
no
Professor
problem. Started.
Gopakumar we can start.
Yeah.
Just a moment. Okay, so yeah, Professor Gopakumar, we are live. Yeah.
Okay. Great. Good evening, everyone. Welcome to this inaugural episode of the Vigyan Adda of the ICTS. I see a good turnout for this Adda, over nearly 100 people on Zoom and perhaps more on YouTube and so on. So this is a new series that we have launched. It's interesting that we are holding it today on the birthday of Ramanujan. It's also, I guess, celebrated also as National Mathematics Day today. And in fact, the topic of today's talk, black holes, even though that's in physics and not mathematics, but surprisingly, a lot of Ramanujan's work has also entered in the understanding of the microscopics of black holes. So it's in some ways an appropriate topic also for that day. I also wanted to point out in this context that today we have an embarrassment of riches. We have at 7:30 p.m. Again, on the occasion of the Ramanujan birthday, ICTS is co-hosting a talk by Manjul Bhargava, the Fields Medalist mathematician, on some of the gems of Ramanujan. So again, accessible to a general audience about some of the wonderful things about his mathematics. You can find the links and more details again on the ICTS webpage. That's at 7:30 p.m. It should leave you enough time for this talk and the Adda afterwards. So let me say a few words. I don't know how familiar the word Adda is to people. I think I definitely heard of it growing up in Kolkata, because that's in a sense the hometown of Adda, but it probably has a wider provenance elsewhere. But it essentially refers to sort of free-flowing discussions, talking about various topics in depth and going and in a sort of a more informal setting. So while ICTS has a number of different outreach activities, our outreach cell also felt that there might be space for an activity which is more of a interactive discussion kind of a format, but in which a speaker sets out some topics often accessible to an undergraduate level. And especially for people who are curious about some of the topics at the forefront of knowledge today, we thought this would be an interesting format to try. And there's so I'm glad so many of you have joined in on this, and there's no better person to start off the series than Suvrat Raju, who is on the ICTS faculty and on a very fascinating topic of the black holes and their connection to the reversibility of time, as you will hear from Suvrat. ICTS has a lot of other events also that if you're in attending it, one of our events for the first time, I would recommend that you check out our outreach page. We have these other events called Copy with Curiosity, which is held once a month, which used to be held in person at the planetarium, which we have suspended for the moment, but we will resume this once the pandemic situation improves. At the moment, we hold it online like most of the other events, and it's called Curiosity During Quarantine. And you can check out some of the previous episodes and upcoming ones on the ICTS webpage. So I think I will invite you to now join the Adda. Before that, I think Rukmini has a more of a formal introduction to make of the speaker today. So I'll hand it to Rukmini.
Good afternoon, everyone. It's a great pleasure for us to have with us Professor Suvrat Raju. He's a theoretical physicist at ICTS who works on quantum aspects of black holes, quantum gravity, and quantum field theory. He obtained his undergraduate degree from St. Stephen's College in 2002, his PhD from Harvard University in 2008. His work has been recognized by many awards, for instance, by the ICTP Prize in 2019, the Sharna Jayanti Fellowship in 2017, the Saraswati Kaushik Medal 2015, and the INSA Young Scientist Award 2013. So it's a great pleasure to have you here with us, Suvrat. So over to you.
Okay, thank you very much, Rukmini and Rajesh, for that introduction. Thank you very much to all of you who've come today. And I'm going to try and hope, that I'll make the next hour or so interesting and worth your time. This is a talk, that's advertised as a talk about black holes and the reversibility of time. But really, the talk, the main message and the main scientific content I wanted to convey is about the modern understanding that we have of gravity and of quantum aspects of gravity. And since this is a talk about gravity and it's directed at undergraduate students, I thought I would start with something that we all know and love and have studied very well in school, which also happens to be, the first understanding that we as a civilization obtained of a precise nature of gravity. And that was the Newton's gravitational law. And the Newton's gravitational law, as all of us know, was obtained by, thinking about the orbits of planets, about the sun. So the orbit of the Earth, for instance, about the sun. And people found now, almost 350 years ago, a little less than 350 years ago, that if you had two objects of this kind, like the Earth and the sun, then you could describe their interaction due to gravity very well by means of a force. And the force happened to be proportional to the product of the masses of the two objects, in this case, the mass of the sun and the mass of the Earth, divided by the inverse square of the distance between them. And this theory was very successful, and it successfully explained the motion of planets around the sun. However, there's something else that's remarkable about this theory. And that is, this theory, in some sense, was developed to understand planetary orbits. But in another sense, it's the quintessential example of a successful scientific theory. And the reason it is such a successful scientific theory is that this simple Newton's law of gravity that we learn in school is actually very powerful. It's surprisingly powerful and happens to hold at a remarkable variety of scales. For instance, if we wanted to describe the motion of a rocket taking off from the Earth, or if you wanted to describe the motion of a cricket ball that one throws up and tries to catch, then those equations are also very well described by Newtonian gravity, even though this theory was developed to understand the motion of the Earth around the sun. Similarly, if you wanted to understand the motion of our own satellite, which is the moon that we see up in the sky every evening, then that orbit is also very well described by Newtonian theory. And if you think about it, this is not something that happens in science all the time. If you develop a theory to understand how, human beings work, then that's not the way, ants function, or that's not the way elephants function. So things in science are often very different at very different scales. But it so happens that this very simple law of gravitation works for a remarkable variety of scales, and it works extremely accurately. And that is the reason, even 350 years after its discovery, it is still taught in a very important way in schools, and because it is so successful. And that's also the reason why in the philosophy of science, this is a law that's held up as an example of something that's a very successful physical law. Now, nevertheless, even though the Newtonian theory is a very successful theory, about 100 years ago, a little more than 100 years ago, people realized that there was something slightly funny about the Newtonian theory. And the thing that was slightly funny was as follows. So remember, we developed the Newtonian theory to describe the motion of the Earth around the sun, but physicists like to do thought experiments. So here is a thought experiment we could think about. What if a huge extraterrestrial giant, this is my giant, came over and pushed the sun a little bit? So, or maybe more realistically, some extraterrestrial civilization came and fired huge rockets at the sun, which caused the sun to move from where it is right now. So the question we can ask is, when does the Earth know that the sun has moved, that the sun is not where we see it in the sky? So, if this giant were to push the sun right now, I see the sun outside my window. How long would it take for us to learn that the sun has moved from its original position? Now, the Newtonian theory actually gives us an answer to this question. And the answer is as follows. Remember that in the Newtonian theory, the force between the sun and the earth is proportional to the product of the masses divided by the square of the distance between them. So if this giant comes and moves the sun, then the distance between the earth and the sun changes. So the square of the distance changes. And so the force that the earth feels changes immediately. And therefore, the earth that is going around in a certain orbit ceases to go around in that orbit and needs to change its orbit. And therefore, the Newtonian theory tells us that if a giant or an extraterrestrial civilization were to come and were to move the sun, we would learn about it instantaneously. With no delay of time, we would learn that the sun has moved. Now, about 110 years, 115 years ago, people realized that this was inconsistent with other discoveries that we were making about physics. In particular, the theory that people developed, the physicists developed at that time, was a theory of what is called special relativity that came from the study of electromagnetism and studying the symmetries of electromagnetism. And it was developed by Poincaré and Lorentz, and some finishing touches were later put by Einstein. And one of the principles of the theory of special relativity was that information cannot travel faster than the speed of light. And therefore, this idea that we get from the Newtonian theory, which is that if a giant were to come and were to move the sun, then we would know about it immediately, is in conflict with this principle that information cannot travel faster than the speed of light. And so, in order to reconcile the theory of gravity with the fact that information cannot travel with the speed of light, and also due to other motivations to understand something called the principle of equivalence, physicists modified this very successful theory of gravity that we had and came up with a new theory that was called the theory of general relativity. Now, the theory of general relativity is actually quantitatively very similar to the Newtonian theory. It has to be that way because the Newtonian theory is so successful, and that is because it is so accurate. And so if one wants to replace the theory of special relativity, the theory of Newtonian gravity, one has to make only small corrections to this theory. And that's because we have checked it in so many variety of scales. But the ontology of the new theory, or rather the description or the philosophy of the new theory of general relativity, was completely different from the theory of Newtonian gravity. So physicists said that, we don't want to talk about the interaction of the sun and the earth in terms of a force between the sun and the earth. Rather, they said, let's talk about a fabric of space-time. This is the fabric of space-time that I've drawn here, on which both the sun and the earth live. And now, why do they interact if there are no forces between them? They interact because the sun causes the fabric of space-time to bend in a particular way. And the reason the earth moves around the sun is not because the earth feels a force that pulls it towards the sun, but rather because, these orbits that the Earth is following happen to be the natural trajectories in this bent space-time fabric. So in fact, if you were to compute in this theory of general relativity, the new orbit of the Earth, the corrected orbit of the Earth, the corrections you would find would be extremely small compared to the Newtonian theory. But you see that the language and the philosophy that we are using to describe now this familiar system is completely different. Of course, the system is not just made in terms of pictures where you draw some fabric of space-time and say some words. There were some precise equations that were written down, on which again Einstein did a lot of work. The equations were finally written down correctly by David Hilbert. Sorry, can you see the screen, Anupam?
Yes, we can
You can see the screen? Okay.
Yes.
Okay. So the equations were finally written down correctly by David Hilbert. And these are the equations of general relativity that can be used to understand the motion of the Earth around the sun. But there are some, you don't need to understand the maths of the equations. There is a very simple slogan that can be used to capture these equations. And the slogan is simply that matter tells space-time how to curve. That's the first equation. So in the picture on the previous slide, the matter that the sun had was telling the space-time how to curve. And then the space-time tells matter how to move. So once the space-time has been curved by the sun, that curved space-time tells matter, which in this case is now the Earth, how to move. And these two equations together can be used to derive very accurate quantitative predictions from this new theory of gravity, which has been checked and is even more accurate than the Newtonian theory in terms of describing the world around us. Going back to the question that I started with, which I said was one of the reasons you could motivate the theory of general relativity, you could ask once again, in this theory of general relativity, what would happen if this giant were to come and were to push the sun? So you see now, because we are not talking in terms of a force, the description of what would happen is rather different. The description of what would happen is that when the giant pushes the sun, that pushing of the sun causes ripples in the fabric of space-time. These ripples propagate at the speed of light, and so it takes 8 minutes for these ripples that you see here for them to travel, just like ripples in a pond travel if you throw a stone in the middle of a pond. And so it takes 8 minutes for these ripples to travel and to reach the Earth. And so the theory of general relativity tells us now, consistent with the fact that information cannot travel faster than the speed of light, that if a giant were to come and were to move the sun, we would not know for 8 minutes. So if a giant has already done so right now, we would not know for the next 8 minutes till we are a little bit further into the talk that the sun has moved. Okay? So this reconciles this aspect of the Newtonian theory, which was in some sense what you can call an aspect of non-locality. So the Newtonian theory, you can say, is a non-local theory. And by inventing now this medium, which is this fabric of space-time, the theory of general relativity is what one might call a local theory. Okay. So now, once people had the theory, of course, they followed it. This always happens in science. Once one has a theory, one has to follow it and see where it leads. And so the German mathematician Karl Schwarzschild found rather remarkably, very soon after the theory was published, an exact solution of the equations of motion that I showed you some time back. And this exact solution is called the Schwarzschild solution. It's some solution that tells you how this fabric of space-time curves. And once again, the details will not be important for the talk, but here is the solution for those of us who know how to read line elements. But this is basically some solution that tells you how this fabric of space-time curves. There's a remarkable side story about Schwarzschild. Schwarzschild actually found this solution when he was serving in the German army during the First World War. And unfortunately, he died very soon after that due to a disease he contracted on the front. So I often, in fact, hold up the story as an example of the futility of war and the dangers of militarism to the advancement of science and culture. But in any case, while he was serving and before he died of this unfortunate disease, he found this very remarkable solution, which we continue to use even 100 years later. Now, this solution, if you study it, has some remarkable properties. You can, this is a cartoon of the space-time I showed you previously. The thing I showed you previously was the precise equation that describe this curved fabric of space-time. But here is the diagram of the same fabric of space-time. And if you look at this solution carefully, you find that it has two distinguished spots. One distinguished spot is what one might call the horizon. This horizon is at a spot which is, this fabric of space-time has some mass like the sun in the center, which is causing it to curve. And there's a horizon which is roughly twice over the mass in natural units, multiplied by the Newton's constant and divided by c squared. And this horizon has the property that if you're an observer who crosses this horizon, you see this ring here, then there is no way for the observer to return back to ordinary space, which is this red area here. And this solution also has something called a singularity, which is this place here, where in fact the solution, the curvature becomes infinity, and so any observer gets destroyed. In fact, a lot of this talk is going to focus only on the horizon and not on the singularity. And if you go far away from both the horizon and the singularity, then you find that this solution, this curved space-time, looks a lot like our world where curvature scales are weak. So when this solution was first found, you see it has all of these unusual properties. And when it was first found, people said, well, okay, you found some solution to some equations of motion, but maybe this doesn't describe anything in the world around us. And you see, it could happen, right? We could write down many kinds of solutions to various equations, and it doesn't mean that nature necessarily does us a favor and realizes these solutions in a real life example. However, one of the remarkable discoveries of the past few decades has been that in fact such solutions, such black holes exist, and they kind of surround us all over in the universe. In fact, wherever we look in the sky, there are black holes. For instance, the Nobel Prize earlier this year was given to Andrea Ghez and Reinhard Genzel for discovering a supermassive black hole in the center of our own galaxy, in the Milky Way galaxy, that one can still see if one goes to a dark spot of the sky. And this is a black hole which is much more massive than the sun. It's 4 million times as massive as the sun, and it's about 26,000 light years away from where we are. This is not the only black hole around us. There are other black holes that one can see that are further away in other galaxies as well, and some of them are even more massive than this black hole Sagittarius A star. For instance, this is a picture captured by the Hubble Space Telescope of a black hole that's 100 million light years away in a distant galaxy, and it has a mass that is 500 million times as big as the sun. So it's even bigger than this black hole that lives at the center of our galaxy. It's not necessary that all black holes have to be these gigantic black holes which are millions of times more massive than the sun. For instance, here is a black hole that's much smaller. It's only 14 times as massive as the sun. It's in our galaxy, and it's about 40,000 light years away from where we are. This black hole is quite an interesting black hole. In fact, some of its properties were studied while I was a graduate student by other graduate students who were in the same class as me. And the properties of this black hole are very interesting, and they're the following. Black holes are not only can sit in one place, they can also turn around their own axis. And this black hole has the property that it's turning about its own axis so fast that its horizon is almost moving at the speed of light. And that's about the maximum angular velocity at which a black hole can turn about its own axis. And this black hole almost saturates that bound. So it's almost what's called an extremal black hole. And it's obscurely named according to these conventions that astronomers have that I don't understand, GRS 1915. Okay. For a long time, a lot of our understanding of black holes came by looking at electromagnetic waves of various kinds, whether looking at radio waves or looking at infrared or sometimes looking at optical signals from black holes and the phenomena around them. But about 5 years ago, we found that in fact we could examine black holes in a completely different way by looking at gravitational waves. So remember, I told you about these ripples in the fabric of space-time that would occur, if a giant came and pushed the sun. In fact, these ripples in the fabric of space-time do occur. They're not fictitious, and they were observed for the first time about 5 years ago by the LIGO observatory, which detects gravitational waves. And what these ripples in the fabric of space-time do is that they cause these gigantic interferometer arms, which are about 3 kilometers, to move by a tiny amount, by 10 to the minus 19 meters, which is much smaller than even the radius of a proton. And the remarkable feat of experimental science is that these very tiny movements, or bending and stretchings of these arms could be detected, and that's given us a new window to observe black holes and other exotic objects in the universe. Now, in fact, the story of black holes and how they're observed and how they're studied is a fascinating story, and there are colleagues of mine at ICTS who study this. I'm in fact not someone who studies how black holes are observed, and this is in fact not even my area of expertise of understanding how black holes are observed. The kinds of questions that I think about and about which I'd like to talk about for the rest of the talk are much simpler, and those are theoretical questions about black holes. So the kinds of questions that theorists like me study are about what one might call vanilla black holes. So these vanilla black holes are ones where you don't have all of these accretion disks or these other black holes to collide that lead to all of these signals, but rather you just have a single black hole that's just living in splendid isolation somewhere in the universe. And at some point, you have a single star that's living in splendid isolation somewhere in the universe. At some point, the star runs out of fuel and it starts collapsing under its own mass, and it becomes smaller and smaller. At some point, the star crosses this radius, which is called the event horizon of the star, and then it just continues becoming smaller and smaller till it just collapses to become this very tiny point. So this is, in some sense, a very simple process compared to all the remarkable astrophysical processes that I showed you. But I'm going to try and persuade you in the next 20 minutes or half an hour or so that, in fact, this process also has many interesting theoretical questions that can teach us a lot about gravity and about quantum gravity. Okay. So, in fact, when we discuss these processes, it's not convenient to keep drawing a sequence of cartoons of a star collapsing. And often the way we draw these processes is by means of what one might call a space-time diagram. If you've not seen this diagram before, it's not very complicated to understand. All that I've done is I've plotted on the y-axis time, and then I'm just plotting the evolution of this star which is collapsing as a function of time, which you can see as it moves up. In fact, there are several Indian physicists who had a very important role to play in understanding how this dynamics of this process works. In fact, one of the first people to write down a solution of this kind was a Bengali physicist named B. Dutt, who wrote down the solution before the two physicists after whom the solution is commonly known, before Oppenheimer and Schneider. But in fact, very little is known about Dutt's life. So I don't even have a photograph to show you because very little is known about him. But there is this paper that he wrote which described for the first time how such a solution could work. And then in understanding the properties of this solution, the physicist A.K. Rai Chaudhary, who's the one on top, was very important. And often when physicists try and understand this kind of gravitational collapse, they don't use this complicated model of dust collapsing, but they use a much simpler model of collapse, which was developed by P.C. Vaidya, who is the gentleman you see below. And so this is the kind of process that we're going to think about, once again, using thought experiments as we go forward. Okay. In fact, I'm going to do a little bit more. I'm going to make my diagram a little bit fancier. In the previous diagram I showed you, I had some star which was collapsing, and I had time on the y-axis. We can do a little bit more. We can rescale the x and y-axis a little bit so that rays of light go at 45 degrees. If one does this, one gets what is called a Penrose diagram, named after Roger Penrose, who was the other recipient of the 2020 Nobel Prize. And this is a third diagram of the same cartoon that I showed you previously, now plotted just by rescaling the x and y axis so that light rays at 45 degrees. And here you see the horizon, which is this purple or violet line here. And the reason also you can see that once an observer crosses the horizon, an observer can never return back to ordinary space, which is here, is that the horizon is itself like a ray of light. And you can easily persuade yourself that once a ray of light crosses you, there is no way for you to catch up with it again. Even if you were to shoot another beam of light after the beam of light that's crossed you, you can never catch up with it. And that's the reason if you have an observer who jumps into this black hole and crosses this horizon, the observer can never recross the horizon and come back out. So we'll draw these diagrams, and as I said, there's nothing to be scared about. These are just diagrams where time goes on the y-axis, and I've rescaled x and y so that light rays go at 45 degrees. So this is a light ray, which is the horizon. Okay. So now, once again, we can do thought experiments, which physicists are very fond of. And so our friendly giant is back to assist us with the thought experiments. So the kind of thought experiment you could ask is, well, I said that we were discussing this star which lived in splendid isolation in the universe. But now, apart from the star, I'm also going to add the giant, and I'm going to give the giant a few planets, maybe the Earth. And I'm going to ask, what happens if you have this black hole, which was formed by the collapse, which you see here? And what if our friendly giant comes and throws the Earth or throws some other ball of matter into the black hole? How does the black hole respond to this perturbation when additional matter has been thrown into the horizon? So on the Penrose diagram, this process looks like the following. You have this star which collapsed, it formed this singularity, here is the horizon, and here is this orange line. We don't plot the giant, of course, but here is the orange line which indicates the trajectory of some additional matter which is falling in after the star has collapsed and is crossing the horizon and is falling into the singularity. Now you can see immediately from the equations that, because the mass of the black hole has increased, and remember I told you that the horizon was proportional to the mass, the horizon grows a little bit because some additional matter has been swallowed by the black hole. In fact, physicists discovered in the 1970s that there were some rather remarkable equations that describe the response of the black hole to perturbations of this kind. And these equations looked a lot like the equations we study in thermodynamics in class 12 and in undergraduate physics courses. And namely, they're the following. Remember, in thermodynamics, you learn that the change in the internal energy can be written by TdS, and then there are these PdV terms, which are called work terms, which exist, but there's also this TdS, this important term. And it turns out that the change in the energy of the black hole, which is the change in the mass, is similarly given by kappa times dA, where kappa is some constant called the surface gravity of the black hole, plus similar work terms that have to do with whether you spin up the black hole or add charge and so on, which are very similar to the work terms that appear in thermodynamics. Not only that, not only is there an analog of the first law of thermodynamics for black holes, there is in fact also an analog of the second law of thermodynamics. Remember that in thermodynamics, in elementary thermodynamics, we learn that the entropy in some of the universe always increases. And in fact, there is a similar rule for black holes. It turns out that sometimes, in fact, the mass of a black hole can decrease. You can reduce the mass of a black hole, but you can never reduce the area of a black hole. And so just like there is a second law of thermodynamics, which tells you that the change in the entropy is positive, there's a second law of black hole thermodynamics that tells you that the change in the area is positive. Now, physicists learned about these equations, and, it looks like we have these black holes, which are, describing some supermassive giants in the center of our galaxy, and somehow they seem to be obeying the same principles of thermodynamics that your morning cup of coffee or tea obeys. Okay? Now, in fact, physicists have seen such analogies before. In fact, I'm sure many of you have also seen them. And that is, for instance, if you read the Feynman lectures in physics, you will see that something that Feynman keeps saying again and again and again, many times, is that the same equations have the same solutions. And many times in physics, it so happens that two different physical systems are described by the same equations. A very simple example of this is if you were to take a mass on a spring with some damping or some friction, that obeys the same equations as an LRC circuit, as a circuit with a resistance, an inductor, and a capacitor. Now, that doesn't mean that a mass on a spring is an LRC circuit, right? Those are two distinct systems. It just so happens that they obey the same equations of motion. And so, you might have thought that maybe, we discovered these laws of black holes. They happen to be the same as the laws of thermodynamics, but that's just the kind of coincidence we see in other areas of physics, where the same equations often appear in many different diverse contexts. Now, one of the remarkable discoveries that was made by Stephen Hawking, in fact, the discovery for which he is most well known, was that this analogy between black holes and thermodynamics is not just some formal analogy of the same equations having the same solutions. Rather, when you think about quantum aspects of black holes, when you analyze black holes, not just within the realm of classical general relativity, but when you add also quantum mechanical effects, these quantum mechanical effects, you can say, maybe somewhat imprecisely, start a fire at the horizon, and this fire burns with a given fixed temperature. This temperature once again has various fundamental constants: the Planck's constant, the speed of light, the Boltzmann constant, the Newton's constant. But the dependence on the black hole for the simplest kinds of black holes we're talking about is just 1 over the mass of the black hole. And so Hawking found that, it is indeed the case that black holes have a temperature, and the reason they're obeying the laws of thermodynamics is not just an accident. It is because black holes are thermodynamic objects with which you can associate a temperature, and you can also associate an entropy, and you can associate other thermodynamic quantities. So there is a way to understand this process, and one way to understand why black holes have a temperature is to think in terms of the fact that when you add quantum effects to black holes, you have a vacuum and there are fluctuations in the vacuum. And these fluctuations near the horizon cause the pair production of particles on opposite sides of the horizon. The particle outside escapes and goes off to ordinary space. This is the green particle outside. The particle inside, the blue particle, falls into the horizon. So if you're an observer who's just living outside the black hole, somewhere here where my mouse is, you would just see a stream of particles, green particles, coming towards you. And so it would look to you that the black hole is emitting photons, just like a fire emits photons at some temperature. Okay? So that's one way to understand why black holes emit particles. Black holes are not really black when quantum effects are added. But of course, there are more precise equations that you can analyze that lead to the formula for the temperature that I showed you previously. It's not, so once again, if you now think of the picture of what a black hole is, you should think of a black hole, once again, not as just a black object into which something falls and nothing comes out, but rather as a black object with this, with this ring of fire around it, which causes it to constantly emit particles at a certain temperature. This fire analogy is a little imprecise. It's a little imprecise because if you have an observer who falls in, this observer will just fall in freely and will not actually see anything when the observer crosses the horizon. But it is true that if you have an observer who's trying to stay at a fixed radius from the black hole, this observer will see this constant stream of particles being emitted from the black hole. It's not just particles which are emitted at the temperature. In fact, black holes obey the entire Planck Blackbody distribution, which is that they emit particles at all kinds of frequencies. They emit photons at all kinds of frequencies. This is the same way that other objects, like if you look at the sun, which I can see outside right now, the sun is emitting photons at a particular frequency. It's emitting yellow light, but it also emits red light, which you will see in a little while when the sun goes down. It also emits blue light. It emits lights in a diverse spectrum. And that spectrum is controlled roughly by a curve of this kind. And this is where the peak is, which is controlled by the temperature. But the black hole, just like the sun, also emits at lower and at higher wavelengths. The difference, of course, between the black hole and the sun is that the temperature of a solar mass black hole is much, 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 much smaller than the temperature of the sun. In fact, if you were to take the formula that I showed you and compute what the temperature of a black hole of the mass of the sun would be, you would find it would be about 6 into 10 to the minus 8 Kelvin, which is very, very, very small. In fact, it's smaller than the cosmic microwave background temperature. Okay. But nevertheless, since physicists are fond of making theoretical questions, one could follow this and one could imagine a black hole that lives in a universe where there's no cosmic microwave background. And one could ask, what are the consequences of the fact that you have this black hole emitting particles at this temperature? Now, all of you know that the energy of an object in relativity, if one formula that everyone knows is that the energy of an object is E equals mc squared. And that tells you that the energy of the black hole is proportional to the mass times some square of the speed of light. But when the black hole is emitting photons or gravitons or other particles, just like the sun is emitting photons or gravitons or other particles, it must constantly lose energy. Now, we have already studied in high school physics and in undergraduate physics the rate at which black bodies lose energy if they're at a certain temperature. That rate is given by the famous Stephan-Boltzmann law, which tells you that there's a Stephan's constant, and then that's multiplied by T to the power 4. This is the temperature multiplied by the area. And therefore, just by conservation of energy, if the black hole is emitting energy at this rate, it must be losing mass at the same rate. And therefore, there's an equation you can write for the rate of loss of the mass. And that just turns out to be proportional to 1 over the square of the mass if you put in the formula for the temperature and the area, multiplied with some constants which I have written down in SI units. Now, in particular, if you were to follow this and you were to ask, what happens after some time, you will find that in a time which goes like the cube of the mass of the black hole is just completely gone. It's evaporated away. Okay. Now, here is a formula for the lifetime of the black hole, once again in SI units. Maybe to give you a sense of the numbers, let me try and give you a sense of numbers for different kinds of black holes. If you were to take a solar mass black hole, then the lifetime of a solar mass black hole would be very long. It would be 10 to the 67 years, which is in fact much longer than the lifetime of our universe. So solar mass black holes are effectively eternal. But there is nothing that tells you that black holes have to be solar mass. In fact, black holes could be much smaller. I have to say that when I give this talk, I'm many times asked about whether the Bermuda Triangle has a black hole. If the Bermuda Triangle were to have a black hole, and if it were to swallow up a plane which flies through the Bermuda Triangle, then the mass of a typical jumbo jet is about 400 tons. And then, in fact, you could compute that this black hole, even if it was there in the Bermuda Triangle to start with, would evaporate away in about 5 seconds. Now, of course, this is a facetious example. There's no black hole in the Bermuda Triangle. But the point is that if one were to have the technology to make much smaller black holes, and there is nothing that prevents them from existing, like if one could take a big plane or one could take this building and squeeze it into a black hole, then these black holes would indeed, according to our theoretical prediction, evaporate away in a short time scale, which is comparable to human time scales. Okay, now imagine, let's follow this logic a little bit further and see what happens. So you see, think of the life of a star. Okay, so you had a star, and at some point it was young and vigorous. And while it was young and vigorous, it was emitting light and it was emitting heat. And then at some point, it ran out of fuel. And when it runs out of fuel, it collapses. It collapses under its own weight. It forms a black hole. Once it forms a black hole, these quantum effects near the horizon of the black hole take over. They start this ring of fire near the horizon of the black hole. This ring of fire in a very long time causes the star to evaporate away entirely into thermal radiation. So if we believe all the theoretical arguments that I've given you previously, it tells you that you could start with a star and end up by going through this entire process with just thermal radiation at a given temperature, which is just characterized by one parameter, which is its temperature. Now, Hawking, who was the first one who thought about this process, argued that this is a problem, and he said that, look, I have found that black holes emit radiation at a given temperature, and that leads to a paradox which is called the information paradox. And the information paradox is the following: you could start with a first star, one kind of star, maybe the sun, or another kind of star, maybe Alpha Centauri, or a different kind of star. You could form a black hole for both of these stars. Maybe these two stars had the same mass to start with. Then both of them would evaporate into radiation, but the radiation only depends on the temperature, so the radiation would be identical. And that's a problem because both the stars had a lot of information in the beginning. Maybe one star had more hydrogen, maybe the other star had more helium, maybe there were other features in the stars. And the question is, where has all that information gone? And it looks like these time evolution arrows cannot be reversed in this process. And this is a paradox because one of the things that we learn in physics from class 7th is that, reversibility is a fundamental property of physics. Reversibility is true of classical physics. If you shoot a cannonball, not only can you predict where the ball will fall, you can retrodict where it came from. When you do ballistics analysis in crime scenes, this is what people do. At least this is what I believe people do while watching TV serials. You see a bullet which is embedded somewhere, and then you try and back calculate the trajectory of the bullet. So not only can you predict where the bullet goes, you can retrodict where the bullet came from. And that's because given the configuration of a system at one point of time, you can solve the equations of motion both forward in time and backward in time. And this is not only true of classical physics, it's also true of quantum physics. So even quantum mechanics is time reversible. And if it were to be the case that black holes were not time reversible, it would be a fundamental problem. It would tell us that the theory of gravity is not compatible with the theory of quantum mechanics or even very basic tenets of classical physics. So that is the information paradox, and this is the reason why it's such a serious problem. Now, over the past few years, I'm going to try and explain how we understand the solution to this in the next few minutes. We have learned that there is actually a solution to this problem, and the solution to this problem is as follows, and I'm going to try and explain it in as non-technical a way as I can. You see, here is a black hole which has emitted, this is a cartoon of a black hole which has emitted photons, and since I said a black hole emits photons at different frequencies, here's a black hole which has emitted photons of different colored light. In fact, this is a computer-generated figure where these photons are indeed placed randomly. So the position of all of these dots is completely random. And if you were to just look at the position of the dots, you would indeed argue that there is no information in these dots. These dots are just completely random and they don't have any information. But if you were to look more closely and you were to look at probability distributions of joint observables in this distribution, you would find that is not the case. Let me point out to you here the pattern. In this case, if you look very closely, you will see that if you look at a yellow dot and draw a line to this black hole and go to the other side, you will find a purple dot. And if you look at this red dot and draw a line to the black hole and go to the diametrically opposite other side, you will find a blue dot. So in fact, there is more information in correlations between the different photons that are emitted by a black hole than there is in individual photons. These correlations can be extremely small to preserve information. In fact, they can be as small as e to the minus s, where s is the entropy of a black hole, which, as I said, just like a black hole has a temperature, it has an entropy. And these correlations can be as small as e to the minus s in order to preserve information about the initial state. This might sound like something fancy, but in fact, it is not something fancy. You see, even in classical physics, if you take some isolated glass of water and you shake it with a spoon, after some time, the glass of water will settle down and it will look like you had not shaken it at all, because the energy that you injected into the glass will all get dissipated into the random motion of the molecules of the glass of water. But if the glass is isolated, if it really is not interacting with its environment, then all the information about how you shook it, how fast you moved the spoon, and everything is recorded in the motion of the molecules of the glass. It's recorded not in the motion of individual molecules, which are all random, but in correlations, in delicate correlations between the different motions. And in fact, those delicate correlations are also of the same order, e to the minus s. So this is the process that we call thermalization, which we see happening all around us. Many times, if you roll a ball, the ball goes and stops, and you might say, where did the information about how fast I threw the ball go? And it went into the random motions of the molecules of the ground and so on. And if you were to observe them very carefully at an accuracy of e to the minus s, you could reconstruct all the details of how fast you had thrown the ball initially. And in fact, we now believe that this is exactly what is happening with black holes, that although it is the case that individual photons that are emitted by the black hole are random, if you look at delicate correlations between different quanta emitted by the black hole, those delicate correlations at a very high accuracy retain information about the information that went into the black hole. Now, there is, in fact, however, a slightly more sophisticated question you could ask about these correlations. Let me just say that, and then I can conclude. You see, you could have asked, well, I said something about the ball and how the ball rolls and stops and how that information is transmitted to various motions of the molecules in the ground. But you could have said, well, if one thinks about the process of black hole formation and evaporation, if you think back of the Penrose diagram I drew, you could have said, well, look, here was this ball of dust which collapsed and formed a black hole. And the ball of dust had become pretty small by the time the black hole started evaporating. And this Hawking radiation was all getting emitted from the horizon of the black hole. So here are some Hawking quanta that are getting emitted. Here's this quanta B that's going and joining these quanta A. And you could say this horizon doesn't actually have contact with this dust that formed the black hole or the information that formed the black hole. So how is information transmitted from where it is, which is here, to where the Hawking radiation is being produced from, which is somewhere here near the horizon. And so it looks like, although in principle, you could store information in these e to the minus s effects, in these very small effects, you could still ask, or Hawking could still ask, how is it that information is transferred to the Hawking radiation that's emerging from the horizon? So now there is actually an answer to this as well, which I'll try and explain as non-technically as I can. You see, we tend to think in terms of objects which are localized. But in quantum mechanics, we know that, it's not so easy to localize objects. And the reason it's not so easy to localize objects is because of a famous principle in quantum mechanics that I'm sure some of you have heard of, which is called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle tells you that if you try and localize an object in a very small distance, then you have to, its energy spreads out a very large amount. If you try and reduce the uncertainty in the position, the uncertainty in the momentum, and therefore the uncertainty in the energy becomes very, very large. Conversely, if you think of an object that has a fixed energy, which is just an energy, what's called an energy eigenstate, which is just some fancy German word for something which has a fixed energy, then this object which has fixed energy is completely delocalized. It doesn't have a fixed position at all. So to localize objects in quantum mechanics, what we usually do is we take superpositions of waves of this kind of eigenstates so that the waves add up constructively in the middle and they destructively interfere far away. And that gives us a localized wave packet, the same way we construct localized wave packets. But now there is a hitch in doing this in gravity, even though this is something that can be done in quantum mechanics. The hitch in gravity is as follows. You see, in gravity, there is another aspect of gravity which all of you have studied, which is called the Gauss law. The Gauss law tells you that in gravity, the energy of an object can be measured from infinity. So if you have this object here, you might have thought that, the object is there, but we can measure the energy or the mass of the object from very far away without actually going to the object. If you think about this, we do this all the time. We know that the mass of the sun is 2 × 10 to the power 30 kg. Of course, none of us has ever visited the sun, and we shouldn't visit the sun if you want to stay alive. But the way we've measured the mass of the sun is by measuring the gravitational attraction of the sun on the earth. And indeed, this is a general principle in gravity that if you have some mass at some point, then you can measure the energy of that mass from far away, from this Gaussian surface far away, which is what you see here. But now just consider what happens if you put together the two principles of quantum mechanics and gravity that I showed you in the previous two slides. You see, I said that the way you construct localized excitations in quantum mechanics is by superposing different energy eigenstates. But you see, you can't do that in gravity so easily to make them interfere destructively far away, because if you have some matter and you try and superpose, so this sum over AI is just taking a superposition of these different energy eigenstates. If you try and take a superposition of different waves in order to localize this matter here, with every energy eigenstate, there is some correlation. You have to modify the metric far away as well. And so you cannot ensure that there is no energy that goes out far here. And that's because, the metric far away always retains a record of the energy that lives here. And so it's not possible to construct a completely localized excitation in quantum gravity the way you would construct an excitation in ordinary quantum mechanics. And the reason for that, I emphasize, is that energy eigenstates, the energy of an object in gravity, can always be measured far away, and energy eigenstates are delocalized. And if you just put together these two principles, and I can explain more, if there are more questions about this, you cannot create a completely localized excitation by making everything die off destructively at large distances. And so, in fact, in gravity, the joint probability distribution of the metric and other fields allows us to identify the state from far away. Now, what I said was technical, but in fact, there is a simple slogan for those of you who found the technicalities hard to absorb. And the simple slogan is as follows. In a theory of quantum gravity, one has what we call a principle of holography of information. And that principle is that if you have information anywhere, even information somewhere in the sun, that information can be obtained by making careful enough observations in a region that surrounds the point where the information is, without actually having to go and visit it. So it's not just determining information about the mass, but even other finer details about the information can be obtained from far away in a theory of quantum gravity because of the features that I explained previously. When applied to a black hole, the slogan is, and this is a slogan which is simple to understand, this principle of holography of information tells us that the region outside a black hole always retains a complete copy of the information that falls into a black hole. So you think that you threw some information into a black hole and it vanished, and indeed in classical physics it would have vanished. Indeed in quantum mechanics without gravity it would have vanished. But in quantum gravity, if you think carefully about how information is localized, by making measurements in this red region, by making careful enough measurements, you can determine, you always have a complete copy of the information that fell into the black hole. And so the bottom line is that information is not lost. People sometimes ask, what was the error in Hawking's argument for the information paradox? And there are two mistakes in Hawking's argument which led to the information paradox. The first error is that Hawking argued that there are simple observables which he calculated which look thermal, but in fact, as we know and as we understand from the physics of thermalization and understand better and better now, just because simple observables look thermal does not mean that the microscopic state has lost information. And in fact, information can be stored in tiny correlations that Hawking did not keep track of precisely. And that's why he was led to the conclusion that information is lost, whereas information is not lost. And the second error, which is the most subtle error in Hawking's argument, is that Hawking assumed that gravity localizes information the way classical physics does, or the way quantum mechanics without gravity does, which is a natural kind of assumption to make, but it turns out to be incorrect on further examination. And in fact, quantum gravity localizes information very differently from classical gravity and non-gravitational theories. And when one adds in this physics that we now understand better, one sees that Hawking's argument that information is lost is not correct. And in fact, the formation and evaporation of black holes is consistent with quantum mechanics, and it is not inconsistent with quantum mechanics. Let me conclude by just saying a few philosophical things. I told you that, if you had some information that was living in the middle here, you could detect this information by making measurements very far away. Now, one has to think of what is the kind of figure or picture one can draw from that. And one of the pictures that I find appealing is that rather than talking about a fabric of space-time, one talks about threads of space-time. It's not very precise, but it captures some aspects of the phenomena I described, because if you hold all of these threads in your hand, you can tell what is happening in the middle instantaneously without actually having to go there. If one makes some disturbance somewhere in the middle here, one has to modify all of these threads far away. And second, the information content of this region in the middle is not controlled by the area of the region, but rather by the perimeter of the region. And that's another aspect that this picture of threads of space-time captures very nicely. This is, of course, just a cartoon, but I think it does capture some aspects of how our philosophical outlook on the fabric of space-time has changed. And I'd like to conclude with something which I think is interesting, which is about how our perspectives of gravity and the nature of space-time have been modified over the years. We started out with this very successful theory of Newtonian gravity, which, however, had the hitch that it was non-local. And we didn't like the non-locality. We didn't like the fact that we were talking in terms of a force between the sun and the earth. So we said, we don't like that. We want a local theory. And so we invented this notion of a fabric of space-time. And then we came up with a local theory where things just affected other things which were close by. And there was no long distance action at a distance of the kind there was in the Newtonian theory. But then we thought a little bit more, and we added quantum mechanics, and we came up with paradoxes. Just like here also we had a paradox for the Newtonian theory. And then to resolve this paradox, we find that once again we have to modify this picture of a smooth fabric of space-time, and perhaps go back a little bit towards the old picture where information was delocalized, and now talk in terms of threads of space-time. So I think it's very interesting that we have all of these theories, all of which quantitatively are making ever very small and smaller incremental changes on the older theories, but philosophically are giving us very different philosophical new perspectives of thinking about the world that we live in. So I'll stop here. Thank you for your attention.
Thanks, Suvrat, for this fantastic talk. Now it's time for the Adda. So please ask your questions and Anupam will moderate.
Thank you, Rukmini, and thank you, Suvrat, for this fantastic talk. And at the outset, I must say that we have already collected close to 40 questions.
Okay.
So we might not be able to address all of them.
Okay.
So let me start with the first question. And Professor Suvrat, I'll just post all the questions for your reference on the chat.
Yeah.
As one.
Yeah, maybe if you read them out, because I can't actually see the chat for some
You
reason.
won't be able to see, it's such a long, so I will have to, but
okay.
Just in case, yeah. Yeah. Okay, so let me start with the first question. So Neha Nagraj is asking, is it possible to create and understand fourth dimension?
Create and understand the fourth dimension. I don't know if you're, so we do often talk in terms of four space-time dimensions, where the fourth dimension is time. It could be that we live in a world which has more than four dimensions, more than three spatial dimensions, which may be what the question was. So it could be, it could be that one of the dimensions is non-compact and we don't see it because we are stuck in 3 dimensions. There are these brain world scenarios. It could be that the other dimensions are curled up. Maybe we're like worms who are living on like a pencil, right? So if you take this pencil, maybe we are like living here and we can't see the fact that the pencil has some thickness. That's another scenario that physicists explore. So it could be there are additional dimensions. We don't have any evidence of such dimensions yet, any empirical evidence, but they could certainly exist and they would not be in contradiction with anything. We can't create them in some sense. It could be that the world we live in has more than 3 spatial dimensions.
Okay. Thank you for the answer, Professor Suvrat. Next question is from physics level. Do we also have space in between the atoms, within the atom? So that's the question.
Yes, for sure. I mean, I'm not sure what the sense of the question is, but yes, I mean, you have atoms and there's space between the atoms, sure.
Okay, we'll move on to the next question. Just Chillin is asking, is there a physical quantity that could confirm the theoretical presence of this space-time fabric? That is there a way to confirm that space-time exists the way we think it exists?
Yeah, so that's an interesting question. I'm not sure in what way it was meant, but the theory of general relativity, the predictions of the theory of general relativity have been verified to excellent accuracy. In fact, if you look at the GPS that we have on our phones and so on, even that already uses, corrections that one can think of as coming from general relativity. And there are other very accurate experiments that have been done to verify the predictions of general relativity. Now, the question of the fabric of space-time is really a question of ontology. It's a convenient language to describe the world that we live in, which is in terms of a metric where, you have a metric and you talk in terms of this fabric of space-time. This language is not necessary for the predictions that we actually observe. You could try and describe general relativity in a more inconvenient language by talking in terms of, once again, action at a distance, and you could get rid of the fabric of space-time, and maybe that might be something one might want to explore. But the fabric of space-time is the most convenient way to formulate the physics of general relativity, and the mathematical predictions have been verified to extremely great accuracy. But the fabric of space-time is a crutch. It's a question of ontology, of what we believe there really is, but it's not something that directly enters into some prediction. It's the natural language in which you formulate general relativity.
Okay. Thank you for the answer, Professor. So next question is by Navneet Mishra. In black hole fireball hypothesis, do emitted particles carry information of what's inside the black hole?
In black hole what hypothesis?
He mentions that in black hole fireball hypothesis.
Black hole firewall hypothesis. I didn't talk about firewalls at any point in the talk. I did
fireball.
Black hole fireball. Yeah, I didn't talk about fireballs also. At some point I said there's a fire that starts. That was just a poetic way of describing the fact that from the horizon of a black hole, you see an emission as if, and if you're an observer at a fixed distance, it would look as if particles were being emitted. It's not really a fire, in that if you pass through it, you would not actually see anything. So it only looks like a fire if you're standing at a fixed distance. And for a freely falling observer, you would just fall freely through the horizon without noticing anything. So I never said fireball, but indeed, if you're asking about Hawking radiation, if you compute Hawking radiation, if you do the leading order computation of Hawking radiation, you would find that it looks like it doesn't carry information. But as I tried to point out in the later part of the talk, correlations between different Hawking quanta do carry information. And they carry very delicate correlations between different Hawking quanta do carry information, and carry information about the entire initial state.
Okay, thank you. So next question is by Subhanshu, and he's asking, sir, kindly please tell us at very small level, is the space-time fabric quantized or continuous?
It's a good question. So I don't know if there's some good empirical answer to that. In the picture that I showed you later, that picture certainly lends itself more to thinking about space-time fabric, which you divide up, and in fact you can talk about dividing it up into cubes which are roughly L Planck. There's a very small length which is called the Planck length, which is the length at which quantum gravity effects become important. And indeed, you could think of space, and there are theories which talk about a space-time where you have a discrete space-time which is divided up into these cubes of L Planck. And perhaps the last diagram I showed might have led someone to that picture that space-time is discrete. But on the other hand, I don't know how to make that very precise. And none of the theories that speak in terms of a discrete space-time are very precise. And it's often most convenient to speak in terms of a continuous space-time. That doesn't mean that the space-time really is continuous. Maybe in our world there really is some graininess at a fundamental level. One should be open to that possibility. But we don't have any evidence of such graininess. And it is not even the case that the theories I'm describing necessarily require such graininess. So if you look at the theories of quantum gravity, like string theory, they don't automatically lead to some direct graininess in the space-time, where space-time becomes some quantized lattice. But maybe that's how it is, but we don't have any either empirical or strong theoretical evidence for that. Although, you could draw cartoons, and it might be convenient to think in terms of such quantized fabrics, to ask questions about information content and so on. I don't know if that's a completely clear answer, but that's about the best answer I can give for this. If you have follow-up questions, I'd be happy to answer them.
Sure. So I'll take the last question from the YouTube and then quickly move to the Zoom question. So Devjyoti Ballab is asking how a star overcomes its degeneracy pressure due to Pauli exclusion principle to become a black hole.
Yeah. So there is a limit called the Oppenheimer Volkoff limit, the Tolman-Oppenheimer Volkoff limit, which is when when the mass of a star becomes large enough, the gravitational force is able to overcome all of these pressures, and that causes the star to collapse. So if the star is massive enough, it will collapse into a black hole.
Okay. Now, Sarang in the Zoom chat, he's asking what causes the black hole to rotate at such high speeds? And I'll connect it to another question by Chitwan. He's asking, since light can't reach us from black holes, how is the rotation speed measured from a black hole?
Okay, so those are both very good questions. In fact, both of them have to do with the matter that surrounds a black hole. For instance, if you ask how was Sagittarius A determined to be a black hole, for which the Nobel Prize was given last year, it wasn't by observing Sagittarius A directly. It was by observing the orbit of stars around Sagittarius A and noticing that some stars were orbiting so fast that there had to be a really compact, massive object, and there could be nothing else except for a black hole. That's also true of the light that we see. It's a good question, because I said, we have these pictures that we see of black holes, but if a black hole is black, what do you mean by taking a picture of a black hole? And what you're really taking a picture of is of stuff falling into a black hole, which as it falls emits light and emits electromagnetic or other kinds of radiation. And that's what you really see when you say you see a picture of a black hole. Now, this stuff that is falling into a black hole could also contain angular momentum, and black holes conserve angular momentum just like other objects do. So if you have some stuff with angular momentum that falls into a black hole, that causes the black hole itself to spin. And the dynamics of accretion disks are such that the black hole tends to collect more and more angular momentum, and that is what causes eventually astrophysical black holes to spin, and even spin at very high angular velocities.
Thank you for the answer, Professor Suvrat. Diana is asking, is the evaporation of a black hole into a thermal radiation related to the mass of the once existed star? This is the
mass of the what existing star?
related to the mass of the once existed star? Maybe a star would have. Yeah.
Yes, indeed. The mass of the black hole is the same as the mass of the original star that formed it. There's conservation of energy. So maybe some of the mass is radiated away in the process of black hole formation, but in the end, the black hole is formed with some mass that is related to the mass of the star that formed it, and the radiation is related to the mass of the black hole, and so it's related to the mass of the star.
Okay, thank you. Chetan Kumar is asking, is there a minimum mass of a black hole? What is the smallest mass black hole that we are aware of?
Yeah, thank you. So, the smallest mass black hole that we see astrophysically are much larger, but theoretically, the smallest mass of a black hole is a black hole whose radius is the Planck length, which I already described. And that's a black hole which is the Planck mass. So theoretically, a black hole could be very, very, very small. So it's you could have a black hole of the size of the Earth would be 1 centimeter, but you could go like 10 to the minus 28 times of that. Okay, so you could go down to much, much, much smaller lengths, and you could still have a black hole. And so theoretically, black holes can be extremely small, and that's why at some point I said that if at some point we wanted to do experiments with black holes that form and evaporate, then we would need the technology to form small black holes, and we can form such small black holes. And theoretically, and maybe also in the beginning of the universe or in other violent astrophysical processes, such black holes were once formed. So the astrophysical black holes that we see are all pretty massive, several times the mass of the sun, but there's nothing that prevents black holes from being much smaller than that. It would be very hard to see them astrophysically, but there's no theoretical limit that prevents black holes from being much smaller.
Thank you. Thank you for the answer. I'll move on to the next question. Akash Gugnani asked, when we say that a body is emitting black body radiation, we mean that it is in thermal equilibrium with the surrounding. So if black hole is emitting black body radiation, so black hole is in thermal equilibrium with what exactly?
No, it doesn't have to be, it doesn't have to be in thermal equilibrium. If you have a body which is, if you have a gas, if you have some black body which is emitting black body radiation, it could just be emitting black body radiation into the space that surrounds it, and it would eventually cool down as a result of emitting that radiation and as a result of the loss of energy. So a black hole doesn't have to be in thermal equilibrium with the atmosphere around it. Now, you can think of black holes that come to thermal equilibrium with the radiation around it. In fact, we often study such black holes which live in kind of a space with a box, and then they emit some radiation and they come to thermal equilibrium. Such black holes would not evaporate, because once they come to thermal equilibrium, they're absorbing radiation as fast as they're emitting radiation. But this process of evaporation that I described is one where the black hole never comes to thermal equilibrium. It just emits radiation and it cools down and eventually disappears. And then the radiation just streams away.
Thank you, Professor Suvrat, for the answer. And now Gaurav Kumawat is asking if dA, I think it's change in area, delta A maybe, is greater than or equal to 0. That means change in area of black hole is always positive. How is that accounted for? How that accounts for Hawking radiation phenomenon? I think that's the question.
Thank you. So indeed, so that's a good question. So a very good question. So the change in the area of a black hole is positive is a classical rule. So in fact, if you look at the full entropy of the black hole and the radiation, that entropy looks like some term which looks like A, which is divided by the Newton's constant. So it's a very big term, and then plus some entropy of the radiation. But indeed, if you were to add both entropies, that entropy always increases. So there's a generalized second law which holds also in the presence of a black hole as it's emitting radiation, which is that the entropy of the black hole, which is this area term, plus the entropy of the radiation tends to increase. But indeed, it's true that the area itself decreases. And the rule I wrote down in the beginning, which was dA is greater than or equal to 0, was just for classical physics, where I had not added in the effect of Hawking radiation. If you add that in, then you have to look at this generalized second law, and not just that dA is greater than 0.
Thank you for the answer. Quickly, we'll move on to the next one. Aditi Prakash is asking, do black holes emit radiations only in the frequency of visible light, or radiation in the entire spectrum? Can we decipher any information from the radiations?
Yeah. So if this is a question about Hawking radiation, the Hawking radiation that would come from a solar mass black hole is in the deep infrared. Remember I said that the Hawking radiation, the temperature of a solar mass black hole would be 10 to the minus 8 Kelvin. So that would be, very, very, very high in the infrared. Now you could think of a black hole that was, 10 to the 11 times hotter, which would be a black hole which is, maybe 10 to the 19 kg or 10 to the 18 kg. So that maybe a mass of a mountain. And that kind of black hole would emit radiation in the visible wavelength, if I got my order of magnitude correct right now. But anyway, you could think of smaller black holes which are hotter, which could emit in the visible wavelength. But solar mass black holes do not emit radiation in the visible wavelength, Hawking radiation in the visible wavelength. As I said, there is other radiation which is coming from the accretion disks and so on, which is a classical effect which doesn't have to do with the quantum part of the talk that I gave. And that is for solar mass black holes in the deep infrared, but one could think of smaller black holes where that radiation could be in the visible spectrum.
Thank you for the answer. Akshay is asking, even I have a similar question. So why do gravity waves travel at light speed? First part of the question. Do they arise as a perturbation solution to the coupled matter space-time curvature relation? Also, what is this wave composed of that propagates at this speed?
Yeah. Why do gravity waves travel at gravity? You can think of gravity as also being a massless particle like a photon. So it travels just like the photon at the speed of light. I don't know if a better answer to answer why it travels at the speed of light. It is a massless particle which travels just like electromagnetism at the speed of light. And the second part of the question was what is vibrating? Yeah. So that's the reason why I said the fabric of space-time is a very useful way to talk about things. These gravity waves you really should think of in terms of the ripples in the fabric of space-time that I described in the beginning of my talk. I said there are these ripples in the fabric of space-time. So these gravity waves are like these ripples in this fabric of space-time that are traveling from wherever they were generated all the way up to us.
Thank you. And I think the last part of the question was to what is this wave composed of that propagates at this speed?
Yeah, that was the answer. So it said that this wave is a wave in the ripples of fabric of space-time. So it's a ripple in the fabric of space-time. So it's not composed of some physical, it's not composed of some matter or something that's oscillating. If you think in quantum mechanics, this wave is some graviton that's traveling, but otherwise it's just a wave in space-time. It's an oscillation of the space-time metric. Just like electromagnetic waves are an oscillation in the electromagnetic field, in the electric and magnetic fields. This is an oscillation in the metric of space-time, and that's what is traveling to us. So there's no physical stuff or which is carrying it apart from the space-time itself.
It's the medium, what you're suggesting. Yeah, thank you. So now I should move on to the questions from the YouTube. So there are so many questions that it's okay. So Dev Molya has asked many questions, but I will take one more question here. He's asking, in vacuum fluctuations, aren't virtual particles generated? Virtual particles are not real ones. How real particles are generated out of vacuum without any energy output? This is the question.
Yeah, that's a good question. Usually we think of virtual particles because we say, there's some particles that are emitted and that are reabsorbed. Okay? But in the case of a black hole, what happens is, you have a particle that's created for some time, but they're created on opposite sides of the horizon. And so one of the particles tends to fall in, they can't re-meet again. So one of the particle tends to come out and the other particle tends to fall in, and the particle that tends to fall in is lost and the particle that comes out is seen. But these are real particles that are emitted as a result of these fluctuations. So usually, as I said, you have some particles which are created and then they re-annihilate. So you have some massive particle, it emits some virtual particles, it reabsorbs these virtual particles. These are the kinds of processes we talk about in particle physics all the time. Here something different happens because these two particles that are created can't meet back again. And so, one particle tends to fall in and the other particle tends to fall out. That being said, I have to say that this analogy of thinking in terms of virtual particle creation has its limits. It's not like a very precise analogy. There is a much more precise way in which you can derive the fact that radiation is emitted from a black hole. There's a precise method of doing that, which I didn't describe because it would be too technical. So this virtual particle thing is at best a mnemonic, which gives you some physical insight into why particles are emitted. You shouldn't take it extremely seriously. but it's a good way of thinking about it physically.
Thank you for the answer. And Rukmini had some comment, I think so. Rukmini,
No, I just said maybe a couple of more questions and
yeah. So, Professor Suvrat, you need to tell us how many questions
we
could
can
you?
keep going. We can keep going. I have no problem. We can, as long as you like. Yeah.
I think there are another 4 or 5.
Okay,
as
sure.
per
Yeah,
this.
we can keep going. No problem.
Okay, thank you so much. Thank you so much. So, okay, now Akinchon Kundu is asking, if a signal of information is sent to black hole, what will happen with that information?
If a signal of information is sent to a black hole, what will, if I understood the question correctly, if you throw some matter into a black hole, that matter will look like it fell in, but eventually, well, so there are two things. One of the things I said is that, the information, the region outside, if you make careful enough measurements in a theory of quantum gravity, always retains a complete copy of the information that falls into a black hole. So in a sense, there's, one has to think about quantum information and quantum gravity rather differently from the way we usually tend to think of information. We tend to think of information which goes from here to there and then it's not accessible anymore. But as I tried to explain, there's the principle of holography of information in quantum gravity, which tells us if you throw some information into a black hole, the region outside always retains a copy. It's very hard to access the information outside. You have to make very careful and delicate measurements to read this diary. Earlier you could just have read it in some simple way, but now if you want to use quantum gravity effects to read it, it requires extremely accurate measurements, but it can be done. And so, indeed, there's a copy of the information that falls in. There's always a copy of the information that remains outside. And even as the black hole evaporates, this copy that remains outside always stays. This information that falls in, of course, also influences in the end the Hawking radiation that comes out. So, you could also just ask, what happens if I collect the Hawking radiation that comes out from the black hole later? And that Hawking radiation also contains traces of this information that you threw in the form of very delicate correlations between the different Hawking quanta.
Thank you for the answer, Professor Suvrat. So I will connect it to another question by Titas Pramanik, and he's asking what will happen if the body falling on the black hole is bigger than the size of the black hole?
So there are science fiction stories about this. There's a science fiction, I forget the author. There's a science fiction story about what if you had a really small black hole, like maybe 1 millimeter across. Okay, so 1 millimeter across would be like, it would be pretty heavy, like already 1,000th of the, or maybe just less than 1 millimeter. Say one micrometer across. So it would be like 1 by 10,000 of the mass of the Earth. So it would just be really, really tiny, right? 1 micrometer across. So you could ask, what if you threw this object at somebody? This is actually a murder mystery story. So you see, if you were to throw this black hole at somebody, it would not eat up the whole person completely. It would just pass through the person, and it would cut a 1 micrometer line. It would eat up all the matter that came in its path, and it would go through the other side. So if such an object were to fall, for instance, in the middle of the Earth, it would just go to the middle of the Earth and keep oscillating and keep eating up matter and becoming bigger and bigger. Eventually, it would eat up the entire Earth. But for some time, it would just keep oscillating, and it would, the Earth is much bigger, and it just eats up whatever matter comes in its path. So maybe a few atoms here, a few atoms there, and so on. Okay. So this, in the murder story, is a perfect murder weapon because you throw a black hole, a very tiny black hole at someone. It destroys the person because, it goes through the person's body and destroys all the organs inside. But no one can detect the murder weapon. It's just lost forever. Yeah, so, if a black hole, you have an object which is much larger in size than the black hole just eats up whatever comes in its path and distorts some area around it. But
Okay.
it's not like it can shrink the object around it magically and make it all fit.
There's a question by Arvind Swaminathan. He's asking, does black hole satisfy Stephen Boltzmann law of blackbody radiation?
Yeah, you have a Stephen Boltzmann. I mean, in fact, I wrote down this thing. So indeed, a black hole emits a lot like a black body. If you look at it from outside, it looks a lot like a black body, like an ordinary black body, which is emitting like, radiation at 10 to the power 4 times the area. Yeah,
Okay,
Stephen Boltzmann law is a pretty simple law. It just comes by integrating the Planck black body spectrum. And that's where this formula came from too.
And so this is an interesting question by Amitabh Yadav. He's asking, what are, in brackets, some examples of the implications of solving the information paradox of black holes?
What are some examples of, I beg your pardon?
What are some examples of the implications of solving the information paradox of black holes?
Thank you. So indeed, that's a great question. So this last slide is kind of telling us that. You see, the information paradox is a paradox, and we now believe that we understand the errors in Hawking's argument that led to the information paradox. But what do we learn from it? So what we learn from it, I think, is more interesting lessons about quantum gravity. So we learn how gravity thermalizes excitations. We learn how quantum gravity stores information. So we learn, that when you put together quantum mechanics and gravity, quantum gravity stores information very differently from non-gravitational theories and from classical theories. So that's a general principle about quantum gravity, which holds independently of black holes. We arrived at the principle by thinking about black holes, but it's now a principle that holds in general independently of black holes, and it's maybe something we could test independently of black holes. So it's a general principle about quantum gravity. And there are other aspects of how to put together quantum mechanics and gravity that also flow from thinking carefully about the information paradox. So indeed, the main interest in the information paradox is to learn what it teaches us about quantum gravity. One of the things it teaches us that I tried to emphasize was about how quantum information is localized, which once you have learned it in the context of black holes, you can also use in other contexts.
Thank you, Professor Suvrat. So, connected question by Gayatri Savarkar. We keep on hearing the word information in so many contexts. What exactly does information mean?
Yeah, I was using information in a specific sense, in the sense that, if you have a description of an initial state, that description can be in many languages. In quantum mechanics, the description would be by specifying some wave function of the initial state. In classical mechanics, that information would correspond to the positions and momentums of all the particles that made up the star in the first case. So that is information. If in the end you cannot back calculate, even in principle, the positions and momentums of all the atoms and molecules that made up the star in the first place, then we are in trouble, because that is violating the principle of reversibility of time, which is an important and sacrosanct principle in physics. And so that is what means, that is what is meant by loss of information. So if you have a complete description of the state, that's what you mean by information. And that complete description of the state should remain at all times. You should always be able to predict the future and retrodict the past. And that can only happen, if you can reconstruct all the information that was there in whatever made up the black hole in the first place. And by information, I mean, in this case, a complete description of the state of the system before the black hole formed.
Thank you. Aditya Pandey is asking a question while referring to the talk. He says, sir, please explain the difficulty of locality in which you say about quantization of gravity.
Okay. So, So you see, I said in quantum mechanics, you have to, so that was indeed one of the things So in quantum mechanics, I said, how do you localize excitations? So to localize excitations, you have to create let me go back a couple of slides. You have to create a superposition of energy eigenstates. So, here I have, forget about this G. So, I can't put a finger, but you see my mouse, just ignore whatever is to the right-hand side of the mouse. So in quantum mechanics, that would be a superposition of energy eigenstates, which is just sum of AI, EI. And I'm hoping, since you asked the question, you know some quantum mechanics. And indeed, if you want to create a localized excitation of even a simple harmonic oscillator, this is exactly how you create it. You take a bunch of energy eigenstates, you take a superposition of them, and that gives you some excitation which is localized, like this blue dot that you see here. But in gravity, and what you do when you choose these coefficients so that these energy eigenstates interfere destructively in this region here where you see my mouse moving, and they interfere constructively in this region where the blue dot is. But in gravity, it doesn't work that way, because whenever you have an energy eigenstate for the matter that makes up the blue dot, you also have to modify the metric far away, so the metric far away retains a record of the energy eigenstate. So now you see, if you want to have destructive interference in this region, you can't do that, because initially this sum AIEI of this matter field was cancelling destructively in this region, but once you combined it with the metric, you're not able to engineer this destructive interference in this region. So it's a general property of quantum gravity, which just comes by putting together the Gauss law and the fact that energy eigenstates are delocalized, that you cannot engineer the usual destructive interference of excitations that you engineer in other non-gravitational theories. And that's why information is always delocalized. In this state as well, if you measure the metric far away, so let's say you measure the metric here, and you also measure a joint probability distribution of the metric and this matter field that makes up this blue dot, you would be able to reconstruct the coefficients AI, because measuring the metric would localize you on some EI, and then you could measure this field phi and determine also the phase of this term AI. So I'm assuming, since you asked the question, that you understand some level of quantum mechanics, so that's the best answer I can give at this level of technicality. But roughly, in a slogan, the answer is that in quantum mechanics, you try and you create localized excitations by engineering destructive interference outside a region, but you can't do that in gravity, because you're forced to contend with the Gauss law, which tells you that the energy can be measured far away. And when you combine these two things, it tells you that you cannot have strictly localized excitations in gravity.
Thank you, Professor Suvrat, for the answer. Bandhan Goel is asking, is some kind of collective behavior observed in quantum gravity?
Is some what behavior?
Some kind of collective behavior observed in quantum gravity.
I don't know what that question means. I don't know what the question of collective behavior means.
Okay, we'll move on to the next question then. So we are towards, we are just going through some of the last questions, and it seems that the last questions are a little bit more technical and very longish. Do you want me to go through those questions?
Sure, yeah.
Okay. So, I mean, a very simple question is, what do we know about how quantum mechanical information of interacting particles falling in black hole gets converted in gravitational information on the boundary? Lokendra Rathore is asking this.
So that's roughly a more technical version of what I said here. You have to ask, if you try to create an excitation by throwing in so you have to specify what the initial wave function of this particle that you are throwing in was. And when you do that, you will find that, you will get some disturbances in the metric outside. And you can try and ask that in detail. You can try and ask, what are the observables you need to measure outside some region in order to determine the information inside? That's too technical for this talk, but it is something that you can ask in detail and answer in detail as well. About, if you have some wave packets, what is the kind of protocol that you need to obey outside in order to be able to reconstruct that information? So that's a good question, and it can be answered in detail. But maybe not without adding a lot more technicalities.
Okay, thank you. Pratik Kulkarni is asking, how can you tell black holes are made up of matter? So that's a little confusing.
How can you tell black holes are made up of matter?
Matter from that made out of antimatter. So, and and the second part is, and what are white holes and how are they different from black holes?
Well, so, once again, once you have a black hole from outside, classically, you would just know about its mass. So, you would not know whether it was made of matter and antimatter. Of course, that is part of the information that I talked about. So you would indeed later be able to determine what was the composition of the stuff that made it up. But from outside, you would just know about its mass and its charge and its angular momentum, and not whether it was, well, classically, you would just know about its mass and charge and angular momentum, and not whether it was, made up of matter or antimatter, or whether it was made up of, more hydrogen or more helium, or more anti-hydrogen or more anti-helium. But of course, as I said, in the end, information is preserved, and that information would remain in some very delicate properties of the metric outside, which you could use to read off. But if you're just asking at a gross classical level, then indeed you can't distinguish these things. A white hole is another solution that of Einstein's equations that you can write down, which is the opposite of a black hole. So, instead of there is anti-trap surfaces. So it's a time reverse solution of a black hole. So usually we think of a solution where you have some lump of matter, a star which collapses and forms a black hole. But remember, as I said, classical physics, the equations are always time reversible. So there's an opposite solution, which is one where you have a black hole and the black hole just spontaneously ejects a huge ball of dust, which goes and forms a star. Now this is a kind of solution that is thermodynamically not favored. Now it's a kind of solution of the following kind. We say we throw a stone into a pond and it leads to ripples, and that's a solution of the equations of motion. But there is another solution of the equations of motion, which is where the ripples on the pond converge on the stone and they throw the stone out of the pond into your hand. And that's a solution of the equations of motion, And a white hole is that kind of a solution, where you have something that looks like a black hole and then it just spontaneously emits some ball of dust that becomes a star.
Thank you. Anand Bolivar is asking, is all the information contained in the correlation of diametrically opposite radiative points, or are higher order correlations, example, between groups of endpoints required to construct the information?
Thank you. Yes, of course, endpoints are required. The figure I showed was just a cartoon. I didn't mean it to be taken seriously as how information is stored in radiation emitted from a black hole. It was just a cartoon that was meant to illustrate that sometimes 2-point correlators might have more information than just looking at individualized points. But of course, to reconstruct information from a black hole and its radiation, you would need all sorts of higher point correlators. In fact, perhaps S point correlators, where S is the entropy of the black hole.
Thank you. Neeraj is, it's little unsure what he's pointing towards, but he says also in the context of holography, would this mean that this information paradox can be resolved by studying the correlation functions on CFTs? This is the question.
Yes, indeed. I mean, in the context of ADS-CFT, this is the process of thermalization, where you start off with some matter, it forms some lump of what looks like a quark gluon plasma in the ADS-CFT. And indeed, you have exactly the process of thermalization, where it looks like information about the initial state is lost, but that information remains in very fine-grained features that you can measure in the CFT. I didn't make any reference to that because one can try and answer this question purely in the bulk gravitational theory, without having making or using holography as a crutch. But in holography, there's this is the process of black hole formation is just the process of thermalization. And indeed, once again, you find that information about the initial state is stored in some very high point correlators at e⁻⁻s accuracy.
Thank you. So we'll take last two questions because we are already stretching on time. So, okay. So a recent question is it possible to exit a black hole hypothetically by traveling towards past using a time machine after crossing its event horizon? This is by Vijay Ganesh. And there have been few time machine questions as well, which were a little difficult to understand, but if you could, yeah.
There's no such thing as a time machine. I mean, I don't know how to answer that question. Let's see. I think that this notion of time machines is something that travels into the past is actually not a very good way to think about things. When physicists think about a state, you think about the whole past and the whole future of the state. Okay? So when you think of the whole past and the whole future, there are not two pasts. There is one past, okay? And there is one future. It could even be that something from the future is, there are interactions that go from the future to the past, like in this Wheeler-Feynman theory. But in the end, there is one world line of the particle. So, you think of a world line of a particle that goes from the past falls into the black hole. That is an unambiguous world line where something fell into the black hole. If that person happened to be you, then that's bad luck for the person who fell in. And that person will, in some sense, in a classical sense, get crushed by the singularity. But perhaps the good news is that in some sense, the memory of that person or the information in that person's brain will remain in these quanta, or will remain in some scrambled form outside and can be read off. But from a classical perspective, from the point of view of how the person feels, you just go through and you get destroyed. And the question about the time machine is not really a well posed question. It's an
yes. So I'll ask the last question now. So this is by Rajarshi, and he's asking the Gauss's law, which makes localization of energy using quantum theory difficult in presence of gravity, is also present in electromagnetic theory. How exactly does one resolve this problem?
Yeah, and that's an excellent question. But remember, in the electromagnetic theory, you have both positive and negative charges. Okay, so if you create a combination of a positive and negative charge, you put them together, you can hide that information from infinity. You see, look at what's happening in this slide that you see here. What you have is an energy eigenstate which is delocalized, and that is what has to be correlated with the metric. Okay? There is no such rule that tells you that, so it's indeed true that if you took a charge eigenstate, that would have to be correlated with the electric field far away. But in fact, you can take a positive and negative charge eigenstate, you could localize both of them, and then you would have a localized excitation which was completely neutral from far away. And so the information was completely localized. And indeed, in electromagnetism and in what are called non-gravitational gauge theories, you can localize information. And the simplest way to understand that is that even though there is a Gauss law in electromagnetism, there are both positive and negative charges. And therefore, you can create a neutral excitation. And it's the neutral excitations that are localized. When you localize excitations, even in electromagnetism, the strictly localized excitations are the ones that are neutral. There is no such thing as a neutral excitation in gravity because there is no such thing as negative energy. And that's the difference between gravity and gauge theories and electromagnetism or other gauge theories.
Thank you. Thank you, Professor Suvrat. I must say that it has been a fantastic Adda, Vigyan Adda, with more than 300 people joining us online, and it's difficult to address all the questions. So with that, I will hand over to Rukmini. Thank you, Professor Suvrat. Yeah.
Thank you, Suvrat, for this wonderful session and explaining to us and telling us more about this very difficult but very beautiful concepts. I would like to thank you and for joining us today. And I'd also like to thank Anupam and the AV team and Kavyasri for helping us with us. Let's end today. Good evening to everyone.
Thank you.